I'm here to share with you some of the things we learned while working on various use cases for streaming not only Postgres to Snowflake, but this is one of the main use cases that we tend to see in our customers. And there are some challenges and solutions that maybe you'll find interesting in your own data ingestion pipelines. So I'm Alex, I'm a senior solution architect. My background is actually not in data science, it's more on the software development. I've done mostly software development in the telco industry, and it's usually custom bespoke projects involving low latency, high throughput, geographical redundancy in the multi-region, 3-4 data centers, even more. So, but I tend to see that what I've been doing over these years applies very much to streaming ETL, because these are also high throughput, low latency systems that have to be developed. And I'm passionate about this space of data streaming and event sourcing, CQRS, and this is why I joined Streamkap with enthusiasm. Okay, so what we'll try to cover, we'll give you a brief overview of the setup, how the architecture looks like, and then we'll get into the challenges and solutions. So first we'll talk about backfill, because 99.9% of the use cases, customers want their initial data to be loaded and then the streaming to start. Then we'll talk about challenges on the source in the Postgres, challenges on the destination, and challenges that are more related to the overall pipeline and the mapping between source and destination. And I hope we'll be able to cover all of it in the allotted time. So first of all, an overview. Why are we doing this? So basically we are doing streaming ETL. So there is, the first part is change data capture. So we need to read the transaction log of the source database is Postgres in this case. Of course, there are other sources like Elasticsearch which don't map necessarily to this model, but 99% of the sources are mapping to this model. So we are reading the transaction log, we are taking all insert, update, delete events, and we're streaming it to a destination. So why would we want to do this? So we want to do this because there are multiple advantages. So first of all, many use cases would benefit for lower end-to-end latency. Of course, many use cases are fine with batch. But we've seen many customers that really want to adopt this model, and it's actually cheaper. So we will see later in some slides, we will share a customer success story, and you will see that it's actually quite cheaper to go from batch ETL to streaming ETL for their particular use case. There are some other advantages. The initial backfill can put a lot of pressure on the database, but once you start streaming, actually it's the load on the source database, which is usually a real-time transactional production database, it's much lower than with batch ETL. So it's preferable from that standpoint also. And you might want to use the stream of events for other use cases. It enables event sourcing, CQRS, all kinds of architecture when you need historical data, and not only the latest view of your current data. So this is the setup. So basically you have Postgres, you have the transactions log that has to be enabled on the source database, and Debezium is actually the de facto standard which is used by this platform to read the transaction log and stream events through Kafka to the destination. So all the events are persisted in Kafka, and then the Snowpipe streaming-based Kafka connector for Snowflake is responsible for taking those events from Kafka and materializing them into Snowflake. So this here is the most common use case that we see when we stream the whole event history into Snowflake, and then in Snowflake it is post-processed and we have the latest view of the data created with dynamic tables. You will see that there are other ways to do it, but this is the main setup that we tend to see, and is preferred by the customers. With Flink, there is in-stream transformations. Currently, for this particular setup, I'm going to talk more about workarounds that we do with Flink to help with the various issues that we encountered in the ingest pipelines. But we can do also joins, enrichment, all kinds of transformations that we would like to do in the streaming side of things, and you don't necessarily, for some reason, want to do it in Snowflake. So setting up the source. Just here some examples. You have to set up some privileges. You have to set up the replication slot. So once the replication slot is set up, Debezium can start streaming CDC events. So like I said, Debezium is the de facto standard. It's used not only in Streamkap, but in all kinds of other streaming platforms, Airflow, what you name it. It's basically responsible for reading transaction log in a reliable way and producing all the events in Kafka. We can easily achieve sub-second latency with this setup. So usually what we tend to see is 40, 50 milliseconds behind the source. So once the event is happening inside the source database in Postgres, in 40, 50 milliseconds, it's already in Kafka. Provided there are no rare events like snapshots happening, which we'll talk about later. So the 99.9 percentile, it's 50 milliseconds you can reliably expect to see in your source. So just the latency between the event happening in the source and once it reaches the Kafka queue. We are focusing on Postgres, but Debezium supports other databases too. Most of them are transactional relational databases, of course. But there is also Mongo, which we see quite a lot, actually, in our customer use cases. And now we have to set up Snowflake. The same necessary privileges. The warehouse, if it's not created, this is just an example. You can set it up any way you want. And we usually need a key for authentication. We don't use user and password. Why Snowpipe streaming? Like I said, there are other alternatives. There is a connector built from scratch by us, which doesn't use Snowpipe streaming, and it's used for Upsert, for doing merging to statements and not having all the history in Snowflake, but just the latest view. But this is, like I said, the most common use case that we see. People want to use Snowpipe streaming. The main advantage of Snowpipe streaming is low latency and low cost, because it doesn't require a warehouse to be started to load the data. Of course, you'll need a warehouse when you want to post-process the data, but just the cost of Snowpipe streaming is very low. You will see later. So now let's talk about the first challenge, let's call it, the backfill. So you have the Postgres database and you want to stream the data to Snowflake. But first you have to take the available data and start from a baseline. So this is called snapshotting. So there are three ways to do it. Initial snapshots and blocking snapshots are very similar. They basically stop the streaming and they select the data in a huge transaction from the database without any kind of filters or chunking. It just selects all the data from all the captured tables and streams it. And after it is done, it starts streaming the CDC events in real time. Incremental snapshots are a different way of working. They work in parallel with streaming. And let's go through each one and see the pros and cons. So initial snapshots, how they work. They start a transaction, serializable, repeatable read. So you get a consistent view of the data at the time the transaction was started. The position in the log is recorded when the transaction is started. And then all the data is captured from the tables. Once the data is written to Kafka, streaming starts from the position, the transaction is committed, and streaming starts from the position in the log that was recorded when the transaction was started. So these are obviously, they have some pros, right? First of all, it's fast. It can be multi-threading. So let's say we usually see 200 and more tables. We even saw use cases with 500 tables in one database. So Obviously, parallelizing this for 10 threads, for example, can increase speed by a lot. But it comes with disadvantages too, especially for large tables. For Postgres, if it takes a long time for all these tables to be captured, the wall log will grow during this time, and you may end up losing the initial point that you saved. So rather depends. What we've seen is that small to medium tables are safe to do blocking snapshots, but for very large tables like hundreds of millions, even 1 billion and more rows, it's safer to do initial snapshots. We always ran into various issues, either the wall log that we mentioned or stability issues with the Debezium itself or on the source database. Incremental snapshots. So now the incremental snapshots, they run in parallel with streaming. The idea here is that it runs very slowly because it has to split. So first of all, it has to split the table into chunks per primary key. So, and then each chunk is selected by primary key with the where clause. And this is much, I would say, it's reasonable to expect around 1 order of magnitude slower snapshot time than the initial snapshot, the blocking snapshots, but it's much safer. So, and it doesn't put any additional load on the source database. So we tend to see that most customers don't really require very fast backfill. So they are fine with the backfill taking 6 hours, 12 hours, even 1 day, 3 days longer than it could, but not have any stability issues. So blocking snapshots are kind of like initial snapshots, but you can trigger them even after the pipeline has started streaming. So what this does, it pauses streaming. You can trigger it for some of the tables, not for all the tables that are captured. And they work exactly the same way as the initial snapshot. So they start a transaction, they capture the tables, and once the transaction is done, it starts streaming to the CDC data. Same cons as the initial snapshots. For very large tables, it can have unwanted side effects and stability issues. And we've encountered some edge cases in Debezium with restarts happening during blocking snapshots, right? So what actually can happen in the current version of Debezium, in some edge cases, when you restart the connector, it can, after restart, it can consider that it has to do a full initial snapshot and start capturing all the tables, not only the ones that you specified. So they have to be used with care. Now, Snowflake. Once we have the data in Snowflake, we are using Snowpipe streaming, we have all the history. But usually for analytics reports, applications, we want the latest view of the data. So this is usually done with dynamic tables, but like I said, there is also the option to stream directly in Upsert mode. So basically the target tables that you stream to in Snowflake will just contain the latest view of the data and not the historical data. So what are dynamic tables? Sorry, there is a problem with the graphical here. So dynamic tables are declarative data transformations provided by Snowflake. So basically you run SQL and it's Snowflake's job to create a materialized table behind the scenes that adheres to the SQL query that you wrote. And you specify how often you want that data to be up to date. It can be no less than 1 minute. What we've usually seen is around 5 minutes. Everybody is happy with this end-to-end latency of 5 minutes because actually this is the critical factor that decides end-to-end latency, right? If Streamkap has 50 milliseconds on the source and there could be, I don't know, another 200 milliseconds for the data to go through the sync connector, basically the whole end-to-end latency of getting the latest view of the data is dictated by the dynamic table refresh interval. Okay. Sorry. So this is how it would look like, a typical query for deduplicating a CDC stream of events. This is very simple. Of course, not every table has a primary key of ID. It can be very complex, but usually this is how it looks like, right? So we are saying here that we want every 5 minutes to deduplicate the streaming of events by this timestamp, which is called Streamkap TSMS, and this is a metadata column added by the stream connector, by the sync connector of Streamkap platform, with the timestamp of when that event went through the system. So, like I said, we are sharing with you some costs from a customer success story. So, there are two costs here: the Snowpipe streaming costs and the dynamic table costs. The Snowpipe streaming costs, like I mentioned, are very good compared to all the other alternatives across the industry, I would say, right? Because they don't require any warehouse to be started. So if you have dynamic tables that are refreshed every 5 minutes, for example, you would only be billed every 5 minutes because billing is per minute. Snowpipe streaming doesn't require the warehouse to be running anything. So I think here let's focus on the takeaway. I think the cost of roughly $20 to $34 per terabyte, depending, of course, on the number of tables, on the size of the rows, on the number of rows in each table. Things may vary. So comparing it to batch ETL data ingest pipeline that was set up before, end-to-end latency with the batch was 20 minutes. End-to-end latency because of the dynamic tables in the streaming world is 5 minutes. So it's 4 times faster, and the overall cost as shared by the customer over a few months of testing and counting was about 3 times cheaper. So that's why I said in the beginning that one of the advantages of using a streaming ETL tool is actually the cost. It seems to be much cheaper, at least for this use case. Upsert connector. Upsert connector, it's not a very complicated thing. It's a Kafka sync connector that is actually doing merge into statements with bulk, configurable bulk sizes. So it takes from Kafka somewhere between depending on how much data is in the queue, it can take between a few hundred and 50,000 to even 100,000 events in a bulk and send them into a merge into statement in Snowflake. Obviously, you will not need dynamic tables anymore because the target tables in Snowflake already have the final view of the data, but you will have to pay the warehouse costs because of the merge into statements. So the warehouse will be always live, it cannot auto-suspend, it always has to be up and running and receive those merge into statements and execute them. Let's get into some let's say, more technical challenges. So Snowpipe streaming in order to ensure exactly one's delivery guarantees, it maintains the Kafka offsets inside the Snowpipe channels. So what this means is that, for example, let's say there is some decimal precision thing that you want to tweak. You want to move the decimal point, or you want to add more precision, or it's an example, and you want to replace some events, nothing will happen on the Snowflake, because if you send the events with the same offsets that you previously sent, they will be considered duplicates and they will not be stored in Snowflake. This is also problematic when you want to do some maintenance on your Kafka infrastructure, right? Because if you want to migrate for example, the Kafka topics, they will change offsets. And if the offsets change, you will have to reset all the offsets in Snowflake to be able to start ingesting the data again from the new topics. So this is maybe one thing to keep in mind. Another challenge can be with the maintaining a good mapping between the source data and the destination data. So usual data types are obviously very easy to handle and very well supported. But there are tweaks done by Debezium when it sees various data types, like the precision of the timestamps, the precision of time-based columns, JSON data, JSON-B data, HStore data, nested structures, nested collections, nested arrays, nested structs, geo data, and that is, for example, on the geo, I specifically put it here because it's not translated to a Snowflake geometry column, it's translated to a variant type of column currently, and this is, for example, one thing that we are working to improve, both on Snowpipe streaming world and in the Upsert connector. Let's talk about failures a bit. So what happens, for example, when there are issues on the destination side? So on the destination, there are tools which retry a few times, let's say batch ETL tools, and if, for example, the outage on the sink is more than 15 minutes, 30 minutes, they will just stop, and they will require manual intervention to get started. This architecture that we present right here doesn't have this downside. So if the destination cannot, for some reason, process events, Kafka is well able to keep days and days of events persisted, and when the destination comes back online, it can start consuming those events. So there will be no impact on the source database, which is actually very critical because it's usually, like I said, a transactional production database which backs up the customer's live applications, and it will, causing issues on that database will for sure have financial impact on the use case. So this is again one maybe should have been one advantage of streaming ETL compared to batch ETL. One thing to note here is that the sink has to have good performance enough to come back and process all those days. Let's say there is an outage on Snowflake for a weekend, right? During the weekend, there will be a lot of events accumulating in Kafka. So those events would have to be processed quickly in order to catch up with the backlog and start streaming the recent data. Currently, both connectors based on Snowpipe streaming and the Upsert connector can easily do 100K records per second. So we have not seen any issues in this regard. Another challenge, perhaps, it could be more of a challenge related to a multi-tenant platform like Streamkap, but not necessarily, because we've seen customers that have easily a few hundred tables and a few tens of databases. Some of those databases can be development or staging databases, and having a good alerting system and understanding if really there is an issue or not when something breaks, it's not always straightforward. So I can mention, for example, RDS instances that stop outside business hours. You will obviously have a broken ingest pipeline because your source database is no longer functioning, but it is not an issue because this is how it is configured. It's a staging database and it doesn't have to work during the night. So what can be done? There are many things that can be done on the alerting and on the dashboarding, but also on the actually the data consistency itself, right? So you can drill down in various visualization and dashboards and try to see, let's say, take the example that I mentioned earlier, the RDS instances. you can drill down and try to see from the metrics and the dashboarding, or you can see by having, for example, the data itself being checked. So you can check counts, destination versus source versus destination. So for example, you can deduplicate the data in Snowflake and compare the counts with the source plus the lag number of events in Kafka, and they should roughly match. And you can do sampling and compare field by field all the data in the source with the data in the destination. Another challenge that I want to mention is because it's related to Postgres, is toast. The values larger than 2 kilobytes are stored out of bound, not inside the row, and they are not served through the replication slot if they are not changed. So an update event will not contain the original value, it will contain a missing value if that value is larger than 2 kilobytes. So there are solutions. You can configure the replication slot to send these values anyway, but it will create a very large wall size, and none of the customers wanted this solution in real life, in practice, because it creates a lot of operational challenges for them. So the BZM itself is able to solve this problem, but it selects. So when it finds a missing value, it does a select on the database, but it does so record by record. And if there are a lot of missing values for a high throughput table that gets a lot of updates, it creates a bottleneck. So you cannot really use this solution unless you know those values will not be missing statistically a lot of the times. So the solution they can keep up even with the huge throughput is solving it in stream processing. So this is what Streamkap does. It has a solution based on Flink that can cache the original values, and when it encounters a missing value, it can backfill it with the original value from the cache and solve this problem. For Apache Flink, there are, like I initially said, there are not a lot of use cases right now, because especially for Snowflake, right? If you stream this data to Snowflake, there is a lot of support in Snowflake platform to do transformations, even soft real-time, kind of real-time transformations. But there are use cases where doing transformations in the streaming platform makes sense. So I would mention one of the use cases is, let's say you want to stream your data not only to Snowflake, but let's say you have some other systems that want to enjoy the data, because in event sourcing world, you have to have projections of your data in the most appropriate database for that specific use case. You want to send the data maybe to some ML platform to do some recommendations and engine based on the data. So if you transform it in the destination system, you have to transform it each time. If you want those transforms to be done once and apply to all destinations, then you can do it in the streaming ingest pipeline, and you benefit from the in all the destinations of the transformed data. So I'm taking a bit of a break here to show you the previous architecture, but we replaced the open source solution with the Streamkap platform, and the main benefit basically is you have a managed platform which can mitigate all the challenges that we've talked about and others. So you have performance and load testing that we do and ensure that it can handle even the most complex workloads. You have monitoring out those quality checks that automatically are handled by the platform and alert you if something in your data is not consistent in source versus destination. And you have things like auto scaling to ensure that that costs can be kept, let's say, under control. So with that, thank you.